Hello everyone, so today we're going to go over section 1.3, Infinite Geometric Series. So we'll begin by looking at an example. You can see on the right here we have a square that has been divided into 4 equal squares, and one of them is shaded, and then we repeated the process for as much as possible. So if the original square had an area of 1, then this first square on the bottom left has an area of 1/4. The next square has an area of 1/16, 1/4 of a quarter. And then the next one after that would have an area of 1/64, and so forth. So if we are to determine the area of the shaded regions, the orange squares, as this process continues, we'll have 1/4 plus 1/16 plus 1/64 plus 1/256, and so forth. As we can see here, the numbers that we add are going to become smaller and smaller, and they will converge towards 0. And so what we know about this series is that it will converge. Okay, so now because we are adding essentially an infinite number of terms together, this series that we stated is an infinite geometric series. Another infinite series, such as 3 plus 15 plus 75 plus 375 and so forth, the one that is highlighted right here, it is divergent because the number are going to get larger, so it doesn't approach a constant value. So we are not able to calculate the sum of this series because it's going to keep on increasing. So there are a certain type of infinite geometric series that would have a sum, and that is they have to be convergent. And in order for a infinite geometric series to be convergent, its common ratio must be between -1 and 1, or the absolute value of the common ratio must be less than 1. Okay? So that leads us to the formula for infinite geometric series. Now first we have, of course, from the previous section here, the sum of the first n terms, Sn is equal to t1, which is the first term, and then multiplied by 1 minus r to the n power, divided by 1 minus r. Of course, r cannot be 1. Now, when the common ratio is between -1 and 1, then the r to the nth power was going to approach 0 as n approaches infinity. So it simplifies to just the infinite sum being equal to the first term divided by 1 minus r. Okay, which allows us to do a couple of different things. First of all, we can find the sum of a geometric series. Again, this right here in the box is just the same idea, but kind of condensed. Okay, so let's look at the geometric series A and B in example number 1. So we have -0.1 and then -0.3, -0.9, -2.7, and so forth. So we know that the first term is equal to -0.1. And we want to find the r value because in order for there to be a sum, the r value must be between -1 and 1. So the second term was negative 0.3, and if we divide that by negative 0.1, we will get 3, which means example 1a, the series is divergent, and as such, it will have no finite sum. And that's all we can do. Now, even though if you were to use the formula, it will produce a value, but that value doesn't mean anything. Okay. Now, let's look at the second example. The first term is 200. The common ratio here, this would be negative 160 divided by 200. So the R value would be negative 0.8. Okay, fractions will work as well, but in this case, we're going to use the decimal value. So we know that this infinite geometric series on the right is convergent. It will have a sum that we can find. Okay, let's use the formula here. S is equal to T1 divided by 1 minus R. So T1 is 200, and then we have 1 minus negative 0.8, which means essentially we have 200 divided by 1.8. Okay, of course we can either use a calculator for this, or in this case it's simple enough that we can just use fractions. So this would be 200 divided by 18 over 10. That's what 1.8 is. And of course, we can rewrite that as 200 times 10, all divided by 18, which is the same as 2,000 over 18. We can simplify that to be, let's see, the 1,000 over 9, which of course is the exact value, or we can write this as 111 and a ninth. Okay, so that's what the sum would be for that series. Okay, so aside from applying the formula directly, there's other things we can do. So, okay, example 2. Determine a fraction that is equal to 2.1 and then 6 is repeated. Write as a fraction, m over n. All right, so in order to do this, we first have to understand what 2.16 really means. Oh, sorry, 2.16 repeated. So there's two parts. There's 2.1. That part does not repeat. And then the 0.06. And then there's also plus 0.006. And then plus 0.0006. And that's how we get the repeating sixes. Okay. Right, because if you were to write this out, this would be 2.16 and then repeated sixes. Okay. So essentially, what we did here is to separate those into individual terms. Now, what that does is allows us to examine these terms as an infinite series. In fact, it is an infinite geometric series. It's very important to note. Okay, the first term, sorry, use T1, is 0.06, and then the common ratio is 0.1. right? Because we are shifting the 6 one decimal place to the right every subsequent term. Okay. Now, since we are applying the formula, it might be easier to write these as fractions. So the first term, of course, is 6 over 100, and 0.1 is 1 over 10. Okay. So the next step, we're going to apply the formula. So we have S is equal to T1 over 1 minus R. T1 is 6 over 100, and this will be divided by 1 minus 1 over 10. Okay, so if we did some subtraction here, 1 minus 1 over 10, of course, is 9 over 10. And then we can rewrite this division as a multiplication. So this will be multiplied by 10 over 9. Okay, we can then simplify the fractions a little bit. Let's see here. So give us 2, 3, and then 10, 1. We were just further simplify, this will be just a 1 and a 5. Okay, so after all of that, we are left with 1 over 15. Okay. So to finish off the question, we actually have to add the two parts together. We have the 2.1, which was the first part here, and then the 0.06 repeated. That's 1 over 15 as we found. So if we went ahead and rewrite this, 2.1 is 21 over 10 plus 1 over 15. Okay, the lowest common denominator is 30, so this would be 63 over 30 plus 2 over 30, and that will give us 65 over 30, which we can divide by 5, so this would be 13 over 6. Okay. And if we use a calculator to divide 13 by 6, we will get 2.16 repeated, where only the 6 is repeated. All right, so that's the idea. It's a little bit more complicated question. The key is to separate what is repeated and what isn't, and then to find the first term and then the common ratio. So it's kind of a three-step process. And then we apply the formula and so forth. Okay, so let's continue to the next piece. Sum of an infinite geometric series is 63 over 3. It's just a fancy way of writing 21. And then the first term is 40 over 3. What is the common ratio? Okay. So we have S is equal to T1 over 1 minus R. We know what S is. S is 21. We know what the first term is 40 over 3. And we want to find out what 1 minus R is. So if we get 1 minus R by itself on the left-hand side, then on the right-hand side we have 40 over 3 divided by 21. Like so. So from there, we can rewrite this slightly. This will be 1 minus R is equal to 40 over 3 times 1 over 21. Okay, which can be further simplified. Let's see, this would be 40 over 63. And we could isolate the r by itself, so that will be r is equal to 1 minus 40 over 63. And that will leave r is equal to 23 over 63, right? Because you can write 1 as 63 over 63, and then you can just subtract. Okay, so we found a common ratio, and we expressed it as a fraction. That's all we need to do. All right, one more. Child on large swing is given a big push. She travels 24 feet on the first back and forth swing, and then only half as far on each successive swing. How far in total before the swing stops? Okay. So the 24 here will be the first term. This is T1. And if it only goes half as far each time, then the common ratio is just going to be 1/2. And that's all we need. So S is equal to 24 over 1 minus 1/2. So that will be the same as 24 divided by 1/2, which is 48 feet. All right, so a nice simple one. So we introduced the formula for calculating the sum of an infinite geometric series when it actually works, right? The common ratio must be between -1 and 1. We derived it, make sure that we understand why it works, and then we look at some examples together, including one involving just direct application that was repeated fractions, and then finally just a short word problem here. And that's all we have for today, so thank you for listening.